Day 447 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 2322, minimum score after removals on a tree. The difficulty level is hard, but don't worry because you already know we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, comment, subscribe, and share. And if you need any new Apple AirPods, go ahead and check out that link in the description so you can get you some. Now let's see what the question says. There's an undirected connected tree with n nodes labeled from 0 to n-1 and n-1 edges. You are given a zero index integer array nums of length n where nums of I represents the value of the ith node. You are also given a 2D integer array edges of length n-1 where edges of I is equal to AI and BI. Indicates that there is an edge between nodes AI and BI in the tree. Remove two distinct edges of the tree to form three connected components for a pair of removed edges. The following steps are defined. Get the XOR of all the values of the nodes for each of the three components respectively. The difference between the largest XOR value and the smallest XOR value is the score of that pair. For example, say the three components have the node values 4, 5, 7, 1, 9, and 3, 3, 3. The three XOR values are 4 XOR 5 XOR 7, which equals 6, 1 XOR 9, which equals 8, and 3 XOR 3 XOR 3, which equals 3. The largest XOR value is 8, and the smallest XOR value is 3. The score is then 8 minus 3, which equals 5. Return the minimum score of any possible pair of edge removals on the given tree. All right, y'all, so that sounds pretty confusing at first. So let's take a look at these examples just to make sure that we are doing this problem correctly. So in example 1, we have our input nums equals an array of integers 1, 5, 5, 4, 11. The edges equals a 2D array of integers, first array being 0 and 1, next one 1 and 2, third one 1 and 3, and the last 3 and 4. The output is 9. Explanation says the diagram above shows a way to make a pair of removals. So before we continue with this explanation, let's go ahead and just break this down one step further about what the question is asking, right? So we have this input nums right here. So as you can see, these integers here are going to correspond to the index, right? So 1 is at index 1, so we come up here, find the value 1, and then as you can see, this is 1 at index 0. So as you come up here, you can come to value 0 for index 0, and you see it has a 1 right here, right? That's where this 1 comes from. Then we have at index 1, we have a 5. So we come to this 1 because it's at index 1, and we look above it, it has a value of, or it has a 5 right there. So once again, nums represents the value of the ith node. So it has a value of 5 for index 1. Then we come to index 2. So we come to this 2, also has a value of 5. Come to index 3. So we come right here to index 3 has a value of 4. So we can see it's a 4 right here. And finally at index 4 we come to the 4 and we can see it has a value of 11. So these right here just represents the values that correspond for each value index, and the value corresponds to the node and the value of that node. Then these edges right here represent which nodes connect to which nodes. So as you can see, 0 connects to 1, right here. 1 connects to 2, as you can see right here. 1 also connects to 3, as you can see right here. And 3 connects to 4 right here. So that's how that works. Now let's get into these explanations so we can see how this XOR values work. So when we see this XOR, that means we're going to be working with binary code, and I'll show you how the XOR operator works as well. So first it says the first component has nodes 1, 3, 4. So matter of fact, before we continue, these red nodes, right, or these red lines, these red edges right here, they represent the edges that are removed. So it says we need to remove 2 distinct edges from the tree to form 3 connected components. So right here, these are the 2 edges we remove. We remove this edge and we move this edge. So now this is one component, 1, 3, 4 is one component, and 0 is its own component, and 2 is its own component because we remove these edges. So keep that in mind as we go through this explanation. So it says the first component has nodes 1, 3, 4. So that's 1, 3, and 4 right here. This is the first component that we're dealing with. Boom, which has values of 5, 4, 11. So as you can see, it's a 5 right here, a 4, and 11 right here at the nodes 1, 3, and 4. So its XOR value is 5, XOR 4, XOR 11, which equals 10. So let's just go through this so we can see how the XOR works. So first, say we have 5. So once again, XOR, we're dealing with binary. So say we have 5. So 5, we say 5 colon, and this is 5 in binary, 0, 1, 0, 1. Boom, that's our 5 in binary. Then we have 4. So we need to compare 4. First, we're just doing 5 and 4 first. So we compare that. So let's just say this is 4. 4 in binary would be 0, 1, 0, 0. So now when we use our XOR to compare these, so we could just put the XOR right here. Boom. Right, so after we compare these using our XOR operator, boom. So what the XOR does is if it's a 1 and a 0, it's going to return a 1. And or a 0 and 1, it's going to return a 1. If it's 2 zeros, it returns a 0. And if it's 2 1s, it's going to return a 0. So we can come right here. As we can see, first we have 2 zeros. We have 0 and 0. That's going to return a 0. Then we have 2 1s, 1 and 1. That's going to return a 0 as well. Then we have 2 zeros again. That's a 0. Now we have a 1 and a 0. So that's going to return a 1. And what that is going to do, so that's just going to be 1 in binary, right? So now we have 1. Then, but we're not done yet because now we need to compare the 11, 1 and 11, right? Because as you can see, it's 5, 4, and 11. It's not just 5 and 4. So it'd be something like this. We'll say 5. First, we're going to do this 5, 4. After we do that 5, 4, then we're going to do 11. So boom, that's what we're doing. We just did the 5, 4. So the 5, 4 got us 1, which would be, so 1 is going to be 0, 0, 0, 1. Boom, so that's the 1. But we still have to compare this 1 that we got from 5, 4. So this 5, 4 got us this right here. Now we have to compare this right here to the 11. So for that, we come 11. My bad, let me clean this up for y'all. So then we have the 11. We have to compare that using the XOR. So 11 in binary would be 1, 0, 0, or excuse me, 1, 0, 1, 1. Boom. Then we have our XOR. Just a moment, y'all. Let me get this right for y'all. Boom. So now the XOR. Once again, we're going to compare them. So 0 and 1, that's going to get us a 1. 0, 0, that's going to get us a 0. 0, 1, that's going to get us a 1 again. And then 1 and 1 is going to get us a 0. Boom. So now we have, this is 10. Boom. My bad. Say equals 10. So that's just how this works. That's how the XOR binary operator works. So let's continue. It's going to say, it's going to show us the same thing, but I just wanted to break it down for y'all so you can see how it works. So now we have it says the first component has the nodes 1, 3, and 4 with values 5, 4, and 11. XOR value is 5, XOR 4, XOR 11, which equals 10. So that's how we got the 10 from this right here. We got the 5, 4, and 11 from right here. Index 1 is 5. Index 3, index 1 is 5. Index 3 is 4. Index 4 is 11. So that's where this 5, 4, 11 comes from, and this XOR value, we get 10. Then our second component has a node which is value 0. So remember, we deleted this edge, right? So we removed this edge. So now this 0 is its own component, and it has a value of 1. Boom. Sorry. 1 because as you can see, index 0 has a value of 1. Boom, boom. So now its XOR value is 1, right? Then the third component has node 2, which has a value of 5. So as you can see, we come to index 2, it's a 5. So the node 2 has a value of 5. XOR value 5 is 5, right? So then now we need to score the difference. So the score is the difference between the largest and smallest XOR value, which would be 10 minus 1. So once we do 10 minus 1, it can be shown that no other pair of removals will attain a smaller score than 9. So once we do 10 minus 1, that's going to get us 9. We got the 10 from this XOR value right here with this component right here. Boom, that's how we got the 10. Then we got the 1 from our second component right here, because remember, it's its own component now, because we deleted this edge right here. So 0 is its own component, and that had a value of 1, which with it also had an XOR value of 1, which is the smallest because 1 is smaller than 5. So we take this 1, we subtract this 10, or excuse me, we subtract this 1 from this 10, and that's how we get our value of 9. So I hope that made sense to y'all. Just in case it didn't, let's take a look at example 2. With example 2, I'm not going to break down how the XOR values or how the XOR operator works as I showed you in the last example. So I hope that makes sense to y'all. But we're still going to go through it so we know what the question is asking and what the question wants us to do. So in example 2, we have the input nums equals an array of integers 5, 5, 2, 4, 4, 2. And remember, these represent the values of each node that corresponds to the index. So once again, index 0, it goes to node 0, has a value of 5. Index 1 corresponds to node 1, has a value of 5. Index 2 goes to node 2, has a value of 2, so on and so on. Then we have the edges, which is a 2D array of integers, first one being 0, 1, then 1, 2, then 5, 2, then 4, 3, then 1, 3. And once again, these represent the edges, or which nodes connect to which nodes. So 0 connects to 1, as you can see, boom. 1 connects to 2, as you can see right here, boom. 1 connects to 2, 5 connects to 2, right here. 4 connects to 3, right here. And 1 connects to 3 as well, right here. Boom. Then the explanation says the diagram above shows the way to make a pair of removals. So once again, these red lines are the edges that we are removing. So now we have 3 components. We have 3, 4, that's its own component. 1, 0 is its own component. And 2, 5 is its own component, I believe. Or let's look at, oh well, yeah, 1, 0 is its own component, that's right. And 2, 5 is on, yeah, that's right. So yeah, these are 3 components: this component, and this component, because we removed these 2 edges. So now these are their own components. So let's go through it. The first component has nodes 3 and 4 with values 4, 4. Its XOR value is 4, 4, which is going to give us 0. So this is our first component, 3 and 4. The values are 4 and 4, and that's going to give us, when we use our XOR operator, that's going to give us 0. Boom. Then the second component is 1, 0 with values 5, 5. Its XOR value is going to be 5 XOR 5, which is going to get us 0 as well. So this 1, 0 has value 5 and 5. When we XOR those, we're going to get 0. Boom. Then the third component has nodes 2, 5, which values 2, 2. So once again, 2 and 2 for this component, same values, 2 and 2. So once again, we compare those using the XOR, we get 0. The score is the difference between the largest and smallest value, which is 0 minus 0. We cannot obtain a smaller score than 0, so that's how we got our output of 0. We just had to do 0 minus 0 because the XOR of all of these component values are always going to be 0. 4 and 4 is going to be 0. 5 and 5 is going to be 0. 2 and 2 is going to be 0. And when we subtract 0 from 0, we get 0. So that's why our output is 0. So I hope that makes sense to y'all. And now that we understand the question, let's get into the fun part, the actual solution, y'all. So first thing in the solution we're going to do is first we're going to get nums.count. So we're just going to say, come right here, we're going to say let n equal nums.count. Boom. Then we need to initialize adjacency list for the tree. So we're going to declare a variable called graph, and we're going to set that equal to a 2D array of integers, like that, square bracket, integer, open up the come outside the square brackets, open up the parentheses, and it's gonna be it's gonna be repeating, colon, a blank array, comma, count, colon, n. Boom. Come underneath that, we're gonna build the undirected graph from the edges. So we're gonna say for edge in edges, we're going to open up the brackets, and we are going to say let u equal edge square bracket 0, comma, then we're going to say b equals edge square bracket 1. Boom. Then we're going to come underneath that, and we're going to say graph square bracket u, and we're going to say dot append v. Come underneath that, we're going to say graph square bracket v dot, excuse me, that should be a dot append u. Sorry, open up the parentheses, u, just like that. Now we need to store our XOR of the subtree rooted at each node. So for that, we come underneath this for loop, and we declare a variable called XOR. We're going to set that equal to an array of integers, square bracket, and open up the parentheses. That's going to be repeating, colon 0, comma, count, colon, n. Now we need to track the parent of each node for our depth first search tree. So for that, we come underneath that, declare a variable called parent. Once again, set that equal to an array of integers. Come outside of that, open up the parentheses. This is going to be repeating, colon, -1, comma, count, colon, n. Boom. Then we're going to come underneath that, and we need entry time of each node in the depth first search traversal. So we're going to declare a variable called end time. End time equals, that's going to be an array of integers again. Come outside of that, open up the parentheses, repeating, colon, 0, comma, count, colon, n. Then we need the exit time of each node in the depth first search traversal. So we're going to declare a variable called out time, and we're going to set that equal to an array of integers. Come outside of that, open up the parentheses, repeating, colon, 0, comma, count, colon, n. Boom. Then we just come outside of that and declare a variable called time, and we're going to set that equal to 0 to start. Now we need to start our or create our DFS function. So for that, come underneath that, we're going to say func, open up the parentheses, or excuse me, don't open up the parentheses yet, func DFS, then open up the parentheses, underscore u, colon, that's going to be an integer, comma, underscore p, colon, that's going to be an integer as well. Come outside of that, open up the brackets. First thing we're going to do, we're going to say parent square bracket u. We're going to set that equal to p. So that equals p. Boom. Then we're going to say XOR square bracket u. Come underneath that, and we're going to set that equal to nums square bracket u. Boom. Then we're going to come underneath that, and we're going to say increment time by saying time plus equals 1. Come underneath that, we're going to say n time square bracket u. We're going to set that equal to time. Boom. Then we're going to come underneath this, and we're going to say for v in graph square bracket u. Come outside of that, open up the brackets. We're going to say if y equals P, then we're going to open up the brackets and say continue. Then we're going to come underneath that, and that's going to avoid traversing back to the parent. Then we're going to come underneath that, and we're going to say DFS, open up the parentheses, V, comma, U, come underneath that, and our XOR for our current subtree with the child subtree is going to be XOR square bracket U. Then we're going to come outside of that, use our XOR operator equals XOR square bracket V. Boom. Then we could come outside of this for loop, and we're going to say time plus equals 1. Just like that. Come underneath that, and we're going to say out time square bracket U. We're going to set that equal to time. Boom. Now we need to run our DFS starting from node 0 or the root node. So for that, we come outside of the function, and we could just call DFS, open up the parentheses 0, comma, -1. Come underneath that, and we need the total XOR of all values in the entire tree. So we're going to say let total XOR equal XOR square bracket 0. Then we need to initialize the result to a large number just to start. So we're going to declare a variable called result and set that equal to int.max. Boom. Now we're going to create a helper function to check if U is an ancestor of V using in time and out time from the Euler tool. So for that, come underneath this, we say func is ancestor, open up the parentheses, underscore U, colon, int, comma, underscore V, colon, int, come outside of that, and it's going to return a boolean, open up the brackets. Then we're going to say return in time, square bracket U, is less than or equal to in time square bracket V, come outside of that, and out time square bracket V is less than or equal to out time square bracket U. Boom. That's all for the helper function, but not all for the whole function. We still have more to go. So now we need to try all of the pairs of non-root nodes as cut points. So we're going to say for I in 1 ... less than n, we're going to open up the brackets. And then we're going to say for j in I plus 1 ... less than n, we're going to open up the brackets. Boom. Then we're going to say let, open up the parentheses, a, comma, b, equal, open up the parentheses, I, comma, j. Then we're going to come underneath that, we're going to declare a variable called x, set that equal to 0. Then we're going to say comma, y, set that equal to 0. Then we're going to say comma, z, and we're going to set that equal to 0. Boom. Then for case 1, or if A is an ancestor of B, we're going to say if is ancestor, open up the parentheses, A, comma, B. We're going to open up the brackets, and our subtree is going to be rooted at B, so we're going to say X equals XOR square bracket B. Then we're going to come underneath that, and we are going to say if the subtree is set rooted at Y, or excuse me, subtree rooted at A minus B, then B subtree, we're going to say y equals XOR square bracket A. Then we use the XOR operator, which is that sign right there, that little up caret. We're going to say XOR square bracket B. Boom. Then we're going to come underneath that and we're going to say Z equals, this is the remaining part of the tree, we're going to say Z equals total XOR operator XOR square bracket A. Boom. Now we're not done yet though, because else if B is the ancestor of A, so we come right here and we say else if, we open up that square bracket, or sorry, we say else if is ancestor, open up the parentheses B comma A, then we open up the brackets, we come right here, and this, so if the subtree rooted at A, we're going to say XOR, or X equals XOR square bracket A. Come underneath that, we're going to say Y equals XOR square bracket B, XOR operator, XOR square bracket A. And that's the subtree rooted at B minus A subtree. Then the remaining part of the tree is going to, we're going to come underneath that, we're going to say Z equals total XOR operator XOR square bracket B. Boom. Not done yet, because case 3, if A and B are in different subtrees, we need to handle that. So we come right here and say else, open up the bracket, subtree rooted at A, we just say X equals X or square bracket A. Come underneath that, we're going to say Y equals, if the subtree rooted at B, we're going to say X or Y equals X or square bracket B. Come underneath that, and the remaining part of the tree, we're going to say Z equals total XOR operator XOR square bracket A. Come outside of that, XOR operator XOR square bracket B. Boom. Then we need to compute the score, which is the max minus the min of the 3 components. So we come underneath this else and we say let vals equal, open up the parentheses, or not the parentheses, open up the square brackets, and we say X comma Y comma Z. Boom. Then we come underneath that and we say let score equal vals dot max, open up the parentheses, force unwrap it with the exclamation point, minus vals dot min, put the parentheses and force unwrap it with the exclamation point, and then we track the minimum score over all valid pairs by coming underneath this, and we're going to say result equals min, open up the parentheses, result comma score, and then all we have to do is finally come right here and say return result. Y'all, that should be all she wrote. Let's go ahead and give it a run before we submit it. See what happens. Okay, we have an error, cannot find. So this should be parent, not parent. Let's run it again. See what happens this time. Okay, we have cannot find Y in scope. So hold on now, y'all, for that should be, oh sorry y'all, this should be a V, not a Y. So now let's run this again. Let's see, and it's accepted. So let's go ahead and submit it. Make sure it's still accepted after we submit it. Ooh, look at that, y'all. 17 milliseconds means 100% of users with Swift. That's what I'm talking about. So before we go, y'all, make sure you get one more look at the code. This is the top part. This is the middle part. This is the other part of the middle part. This is the bottom. And yeah, y'all, with that being said, I hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.